If you take a physical cylinder representing a vertebrate neck and twist it 270 degrees, the material fails in the center. The torsion induces immense shearing forces that inevitably pinch and compress the internal structures. In mammals, this type of structural failure is lethal. The severe rotational forces tear the delicate inner linings of the cervical blood vessels, leading to clots and ischemic strokes. Yet the Strigiformes, the owls, routinely execute a flawless 270-degree yaw without triggering any of these catastrophic vascular or neurological failures. Achieving this rotation requires a systemic, multi-layered physiological redesign spanning the entire neck. To understand the mechanics of this rotation, we have to treat the owl's anatomy as a complex engineering problem, dismantling the solid mechanics and fluid dynamics layer by layer. This schematic compares the foundational skeletal structure of a mammal on the left with an owl on the right. Mammals possess a rigid limit of 7 cervical vertebrae. The owl possesses 14. Doubling the number of vertebrae changes the basic physics of the column. It distributes the intense rotational stress into smaller, manageable increments across 14 separate articulation points. But the bones only form the scaffolding. The internal vascular routing is where the distinct evolutionary deviations begin. In most birds, the vertebral artery enters the cervical column at the absolute base, at vertebra C14. The Strigiform vertebral artery bypasses the base entirely. It enters the column higher up, at vertebra C12. Shifting the entry point 2 vertebrae higher removes maximum tension from the base of the neck. This provides the blood vessels with immediate mechanical slack, giving them the physical length required to endure extreme torsion without snapping. Inside the neck, the vertebral arteries are housed and protected by bony, hollow canals within each vertebra, known as transverse foramina. In standard mammalian anatomy, the physical tolerance here is exceptionally tight. The interior bone closely hugs the artery, leaving zero room for lateral displacement. This cross-sectional diagram illustrates the structural difference. On the left, the tight human fit. On the right, the owl's specialized transverse foramina, which are exactly 10 times larger in diameter than the artery passing through them. This 10-to-1 size discrepancy creates vast empty air pockets around the vessel. As the bone twists, the artery freely deforms and shifts within the hollow space. This specific osteological adaptation physically decouples the blood vessel from the bone. It eliminates the precise physiological pinch points that cause strokes in other species. Protecting the vessels from physical crushing solves the solid mechanics problem, but it introduces a fluid dynamics problem at the exact moment of maximum 270-degree torsion. Angiography data from Johns Hopkins researchers reveals a highly unusual biological response. As the owl's head rotates, the blood vessels located directly under the jaw actively expand rather than shrink. These rapidly expanding vessels act as contractile reservoirs. They function as biological fluid capacitors. By pooling excess blood at the base of the skull, they guarantee uninterrupted cerebral perfusion, the continuous flow of oxygen to the brain, even while the lower arterial pathways are temporarily restricted by the twist. Supporting this localized pooling is a secondary fail system consisting of anastomoses. These are microscopic, specialized vessel connections that link the carotid and vertebral arteries into a unified, redundant grid. If extreme torsion completely occludes one primary vertical route, this anastomotic network seamlessly cross-feeds the blood to the brain through alternate pathways. The vascular system guarantees brain oxygenation, regardless of orientation, by relying on dynamic rerouting and localized fluid pooling. The skeletal slack and the fluid reservoirs require a highly specialized myological system to actuate them. The muscles must precisely drive the 14 vertebrae and support the weight of the skull throughout the torsion. The primary biological actuator for this movement is the M complexus, a massive craniocervical muscle that manages yaw and the gross flexibility of the upper neck. This dissection photograph of an American barn owl isolates these actuators. The fleshy tissue labeled C is the M complexus. Rather than anchoring to a single point, it splits into 3 distinct slips that attach separately to vertebrae C4, C5, and C6. Anchoring the muscle across multiple separate vertebrae stabilizes the skull across multiple pivot points, preventing localized muscular tearing during rapid rotation. The M complexus spreads the intense kinetic load of the head's rotation evenly across the entire upper third of the cervical column. While the M complexus handles the upper neck, A secondary major craniocervical muscle, the M. biventer cervicus, manages extreme long-range tension. It has a massive anatomical span. It originates far below the neck in the thorax, specifically at the aponeurosis notari, above vertebra C14, and inserts directly onto the back of the skull. Internally, it is structured as two parallel fibered fleshy bellies, interconnected by a long, extremely thin tendinous intersection. This continuous tendinous cable allows the lower thoracic body to exert direct control over the skull's pitch and yaw, without crowding the mid-neck with heavy, restrictive muscle tissue that would impede rotation. The Strigiform myology balances localized, multi-point anchors at the top with long-range tendinous cables from the bottom to safely execute the movement. This unified visualization tracks the entire biomechanical sequence as the owl executes a full 270-degree rotation. The M. complexus and M. biventer cervices fire first, smoothly distributing the kinetic force across the 14 cervical vertebrae. As the bones twist, the vertebral artery pulls slack from its high entry point at C12, shifting harmlessly into the protective 10 times larger air pockets of the transverse foramina. As the rotation hits its absolute peak, the contractile reservoirs under the jaw inflate to hold blood, while the anastomoses perfectly cross-feed oxygen to the brain. The rotation succeeds precisely because the structural load and the fluid delivery are heavily distributed. At no point does the system rely on a single joint, a single vessel, or a single muscle. Human anatomy presents a stark contrast, which is why clinical data on chiropractic trauma so frequently highlights our extreme vulnerability to rapid cervical rotation. Looking at this split-screen comparison, the human transverse foramina tightly lock the vertebral artery directly against the bone. When a human neck is violently manipulated, the artery physically has nowhere to go. It is pressed directly against rigid bone. Because human anatomy lacks the 10 times air pockets, the contractile reservoirs, and the redundant anastomoses, this intense physical manipulation violently tears the vessel lining. The owl's neck achieves its extreme rotational capacity through strict biomechanical redundancy, engineering its performance entirely by eliminating single points of failure.